Hi, my name is Mark, and in today's video we're going to be looking at question 8 of the higher level 2022 chemistry paper. This is an organic chemistry question, and yeah, let's get straight into it. So taking a brief look at question A here, or should I say, yeah, question A. We're going to have a few parts A, B, I think that's everything in this question, and there's a total of 50 marks going. And this is one of the organic chemistry questions, so, you know, some people... I know myself, I found organic quite tricky when I was studying it. So hopefully when we're going through this, we can go through each part and kind of explain my thinking, my kind of reasoning behind it. And yeah, let's get straight into part A. So looking at part A here, we're going to have a few kind of like subparts here. We're going to have part I, and that's going to be the first one we're going to be doing. In this case, we're asked to explain with the aid of a diagram. So important thing to know here, we're going to be drawing something. And we're asked to explain the acidic nature of the carboxylic acid functional group. So that's one of the groups that you add on, and in this case we're talking about the carboxylic acid group. And yeah, what we're going to do is we're going to draw a little diagram and kind of talk our way around it, and then we're going to have a little paragraph as well, because we have to, it's with the aid of a diagram, which means we both need to include a little bit of an explanation and the diagram. You can't get away with just one or the other. And yeah, let's get straight into that answer. So I've pulled up a little paragraph that I've written kind of explaining the acidic nature of the carboxylic acid group. And over on the right here, I have this little diagram showing off our kind of just actually the carboxylic acid functional group itself. And just a few things to draw in before I go any further. And we're going to have these series of dotted lines and an overall negative charge here on the this kind of like right hand side of the carboxylic functional group. And it's an important thing to note, because this this diagram is going to kind of help reinforce our answer, if that, you know, if that makes sense. So taking a look at the carboxylic acid functional group, this can also be denoted by the kind of like COOH kind of is the group part. You could also write that as just writing it down here, or COOH, and that or is kind of referring to the rest of the compound, and the COOH is just like the bit that you add on. So in our label diagram here, that's what that R stands for. It's actually just the bit that we've added on. And in this case, what we're going to be talking about is the fact that the carboxylic acid functional group, it donates a proton. So the important thing to note there is that it is donating a proton. And when it does that, it creates the carbox ion. And when this happens, this leaves a stable arrangement with a delocalized charge. So that delocalized charge, just to have a little bit of a look at this delocalized charge, it's actually this charge over here on the right hand side that I drew in at the start. And because the carboxylic acid functional group, because it loses that proton, it's forming the ion. And as a result, this ion itself is actually stable because it exists as a resonance hybrid. Now, you don't need to include some of those terms. If you choose to, that's perfectly fine. But in effect, the buzz terms that you really want to include here are the fact that it donates a proton, creating this carboxylate ion, and then as well as that, because it donates that proton, we get a delocalized charge, which creates this stable arrangement. And the diagram on the right here doesn't have to be super complicated. It's just kind of reinforcing our answer. So a little bit of a tricky question to start with, and there was a total of 6 marks going for this. And the breakdown was kind of fairly simple. You got 3 marks for correctly kind of talking about the process that's occurring. So in this case, we're talking about the fact that it is donating that proton and creating the ion. And then you got another 3 marks for including the fact that as a result of it donating the proton, should I say, that ion that is left is actually stable due to a delocalized charge. And our diagram over here on the right is kind of just supporting our answer. So moving on to part 2 of kind of part A here, we're going to be asked another question on our organic chemistry. And in this case, we're asked to give an example of a reaction that demonstrates the acidic nature of ethanol. So in this case, it's just a nice and simple reaction that we're actually required to write down. So it's an example reaction in this case. And there might be a few that you kind of go to straight away, but I'm just going to kind of write down the one that comes to mind first. So in this case, the acidic nature of ethanol can be seen in a reaction with sodium. Now, you mightn't say sodium here. You could also say, you know, kind of any other alkali metal. So just written that down here, alkali metal. So instead of saying sodium, you could have said any of those alkali metals, and they'd also be completely fine. Another way you could do this is by writing down the formula, which I'm going to do now. So in this case, I've just written down kind of a basic formula, kind of almost showing out or describing what I've said here or written down. So when I was saying the acidic nature of ethanol is seen in a reaction with sodium, by writing down this formula, we're kind of reinforcing the idea. So Na, or in brackets I have K here, so it could be Na, you could do sodium or potassium or any of those alkali metals, as I said earlier, and we're mixing that with our ethanol, which is this species here. And I haven't written anything after the arrow, so I haven't done anything on this side of the reaction, and the reason for that is because you're not actually required to know the product. So if you went ahead and tried to figure out the product and you got it wrong, you actually wouldn't lose any marks, which is pretty nice. So the main takeaway here is that the acidic nature of ethanol is demonstrated in a reaction with any alkali metal. In this case, I chose sodium. So there's a total of 6 marks going for this question, and you kind of just got the 6 marks for stating the fact that you need to be reacting the ethanol with in this case sodium or any other alkali metal. Writing down the formula is also a completely acceptable way to get full marks. So moving on to part 3, here we are asked, would you expect to observe a reaction when a drop of pure ethanol is added to damp solid sodium carbonate on a clock glass? And then we're asked to explain. So the things that we need to include here are, actually the important things to include here are, would you expect? So it's like, what actually is happening? Is something happening? Is nothing happening? Is something happening? And then we need to explain our answer and kind of give a little bit more context as to why we think, that reaction is occurring or if it's not occurring. So in this case, the what actually happened, did a reaction occur or did it not? In this case, nothing actually should occur. And the explanation behind that is that ethanol itself is not strongly acidic. So, in other words, ethanol it's a weak acid, it's weakly acidic, and it's not mixing it with the damp solid sodium carbonate. It's not actually going to have any. It's not going to have any reaction. So in this case, that's what was kind of required here to get the full marks. So there's 6 marks going in total for this question, and you got 3 marks for getting each of the parts right. So in this case, the what, and also the explanation behind it. Now, you can't get the 3 marks, the explanation, if you didn't, correctly identify whether the reaction occurred or not. But if you got both of these correct, then you'd get your full 6 marks. So moving now on to part B here, we're going to be moving on to a different kind of like section of the question, and in this case there's going to be all once again several like subparts. So let's just take a look at part B, which says that we're given a pure ester E that has a rum-like aroma, and in part I here we are asked to write a balanced chemical equation for the formation of E from methanoic acid and ethanol. So this is going to be the combination, the chemical kind of equation of methanoic acid and ethanol coming together to create this ester E. And that's kind of what we're tasked here. So the first thing I'm going to do is I'm going to write down the formulas for methanoic acid and ethanol. And then from there we can kind of work our way through the question. But just before we jump into actually solving this question, writing down our balanced chemical equation, there's one thing I want to make a note of first, which is kind of the process of actually making an ester, also known as esterification. And in this instance, I've kind of written down the general formula here, which in this case, when you combine a carboxylic acid, in this case we're looking at methanoic acid, and we also add an alcohol, which in this case is ethanol, you're going to get an ester, and you're also going to get a bit of water there, a water product. So this is something to bear in mind when we're doing out our doing out this question, because that's what we're doing. We're combining carboxylic acid and an ethanol, or an alcohol should I say, in methanoic acid and ethanol, and then we are expecting to get water plus some other ester. So I'm going to go ahead now and write down our formulas for our methanoic acid and ethanol, and then go from there. So I've written down kind of our general equation here, and just to take you kind of through it, this first term here, this HCOOH, this is going to be our methanoic acid, and then moving on from that we have our C2H5OH, which is going to be our ethanol. Now, when we combine those, according to the kind of general form that we were looking at earlier, we're going to be getting an ester and a water product. So this is what the water product is here. And I've just wrote down here ester just because we don't know what that is yet. And there's a couple different ways you could tackle this. You can actually, one of the ways could be drawing out all of the compounds in their structural kind of formulas, and then looking at how they, add together and move around to give you your ester. But personally, I'm just going to do some kind of basic kind kind of basic adding and subtracting, because as we know, the amount of one atom on, for example, the left hand side of the equation has to be the same as that on the right. So if there's, for example, 3 carbons on the left, we need 3 carbons on the right. So what I'm going to do is add up all of the carbons, the hydrogens and the oxygens on the left hand side, and do the same for the other side, and then subtract them to get the difference, and that will be the compound, or should I say, that will be the chemical formula for our ester. So now just drawing out like a little table here. On the left hand side, let's add up all of our hydrogens. So our first hydrogen is going to be here, and then we're going to have a second one here, so it's going to be 2. We have 5, so that's going to give us 7, and then another one which will give us 8. So on the left hand side, we're going to have 8 hydrogens. Moving on from that, we're going to look at our carbons. So there's 1 carbon and another 2 here, so it's going to give us 3 carbons as well. And then moving on from that, we're going to be looking at our oxygens. So there's 1 oxygen, 2 oxygen, 3 oxygens. So we're going to have 3 oxygens on the left hand side. So we know that on the left hand side of this equation is going to be 8 hydrogens involved, 3 carbons and 3 oxygens. And now we're going to approach the problem looking at the right hand side now, and the difference hopefully will be the formula for our unknown ester. So on the right hand side, all we have is, some amount of, all we have is water. So we have 2 hydrogens and we also have 1 oxygen. So just writing that down, we're going to have 2 hydrogens, 0 carbons and 1 oxygen. So what I'm going to do now is subtract the right hand side from the left hand side to give us the needed chemical formula for our ester. So just before I go any further, just to write up here on the right hand side, this is going to have to include our ester, which we haven't found yet. So that's what I'm going to be doing now. I'm going to be moving everything on the right hand side, all of those hydrogens and carbons and oxygens that we found, onto the left hand side, subtracting them away to find our whatever the ester is. So in this case, what we have is 8 hydrogens minus 2 hydrogens. So we're going to have 6 hydrogens. We have 3 carbons on the left and we have 0 on the right, which means that we need 3 more carbons. And then we have 3 oxygens on the left and 1 on the right. So 3 minus 1 is going to give us 2 oxygens. So this is going to be the formula for our ester. Now, if you want to write this in like the correct kind of formula, kind of shape almost for an ester, the way we're going to do that is by writing it as such. So it's going to be HCOOC2H5, and this is going to give us the kind of correct, it's the same, has the same number of hydrogens, carbons, oxygens. We're just writing it so that it looks a little bit more like an ester that you'd be able to kind of recognize when you're reading the equation. So finally, coming back to our question at hand, we weren't asked to find the ester E, we were actually asked to write a balanced chemical equation for the formation of E. So now that we know what E is, we can actually now just rewrite out our equations that we had at the start and now include the ester that we didn't know previously. This means that our final answer is going to look something like this. We're going to have our methanoic acid, which we said was HCOOH. Added on to that, we're going to have our ethanol, which is going to be C2H5OH. And then moving on, once we react those two things together, what we're going to get is our water product. And then we're going to be also left with the ethanoic acid, or not ethanoic acid, sorry. We're going to be left with our ester that we just found there, which in this case is going to be HCOOC2H5, which is a bit of a mouthful, but yeah, that is the correct answer that we need. So there was 6 marks going in total for this question, and the breakdown was fairly simple. You got 3 marks for correctly getting the formula, and you also get another 3 marks for correctly balancing it. In this case, the way I approached this question was by using that general formula, finding the unknown ester, and then just simply balancing it. So in this case, what we can see that on the left hand side and the right hand side, there's the same number of hydrogens, carbons, and oxygens, which means that this is a balanced equation. So moving now on to part 2, here you're asked to give the systematic IUPAC name for E. So in this case, E was the ester that we found previously. So the first thing I'm going to do is actually write down the formula that we had for E, the one that we found, which in this case is HCOOC2H5, and that's going to be our ester E. Now, we don't know how to, personally, I wouldn't be able to, tell you what that is just right off the top of my head. So what I'm going to do is, by using the formula that we have written down, I'm actually going to draw out the molecule, which makes it a little bit easier to name it because you can actually look at the parts in it and kind of deduce from that. So I'm just going to do it in a different color here so that we can see it a little bit more clearly. So what we're going to do is start with this hydrogen on the left-hand side. So we're going to have a hydrogen, which is going to bond to a carbon. Moving on from there, we're going to have a double bond going up to our oxygen and a single bond going down to our other oxygen. Moving on from this single oxygen, it needs another bond to be stable. So in this case, we're going to have it bond to a C, which is then bonded to another C. And coming off of all of these carbons, we're going to have our hydrogens. So we're going to have 5 in total coming off of it. So this over here is going to be our required kind of drawing, if you will. Now, we're not required to do this, but personally, I just find it a little bit easier because I can actually group them and understand a little bit better what's going on when I'm, naming the actual, in this case, this ester. So the thing that you want to do here is actually go ahead and group the important parts of the molecule. The first one is going to be this bottom chunk, which is going to be where we get the first part of the name. And then we're going to be also using this chunk up here, which is going to be used for the second part of the name. So the naming convention of esters kind of follows this strange way of doing it. Instead of naming it by looking at this first piece and then going and then having the second part coming from the second piece, you actually need to start with the second piece. So in this case, the second piece has 2 carbons in it, which means it takes on the appearance of an ethyl group. So we're going to have our first piece of the name being ethyl. And now looking for our second piece of the name, we're going to be looking at this first block here that we have boxed off. There's 1 carbon here, which means it's going to be using the meth prefix. So in this case, it's going to be meth. And then the way that we follow the naming convention for esters is it's going to be methanoate. So the total answer that we're actually required here is going to be ethyl methanoate. So just to underline it there, ethyl methanoate. And the way that we get that personally is by drawing out the structure and then looking at the 2 kind of important groups and using that to get the name. So for part 2 here, there was a total of 6 marks going, and those 6 marks were kind of just attributed to getting the correct answer, which in this case was ethyl methanoate. But I hope kind of explaining how I would tackle this question kind of gives you a little bit more of insight of how you might do them in the future. They can be a little bit difficult to get your head around, but in this case, I always find drawing it out makes it a lot easier for me. So moving now on to part 3 here, we're asked how many carbon atoms in a molecule of ester E are in planar geometry. So basically what we need to do is we need to use ester E, which we were working on in the previous question, and we have to use that to answer this question, which is how many of these carbon atoms are in a planar geometry. Now, planar geometry, just to kind of give you a bit of a refresher, is to make sure that all of the bonds are lying in the same plane. So the way I'm going to tackle this is by taking, copying the structure that we got from the previous question, and from there we're going to try and solve this. So here is our structure of the ester E, which we were looking at before. So just to write that down, this is going to be our ester E here. And what we're going to be doing is determining whether the carbon bonds inside of it are double or single, and by using that we can actually figure out whether they're planar or not. So in this case, whenever there's a single bond, we're not actually interested in it. Whenever they're a single bond, they're not planar. But whenever there's a double bond connected to a carbon, we know that it is that's a planar bond. So in this case, what we have is we have these 2 C's over here on like the bottom right hand side of the molecule as we're looking at it now, and they all have single bonds leading into them. So what that kind of means is we're not really interested in them. However, if we look at this carbon up here on the top left, and just put this little star beside it, what we see is there's actually this, I'm just trying to elaborate it, there's this little double bond here going off to an oxygen. And what that basically means is because there's that double bond, it means that that carbon is going to be in a planar geometry. And as a result of it, and that double bond, as a result of that being there, it means that that is going to be a planar kind of a planar carbon. And the question, if we go back to it, but just kind of remember at the top of my head, the question is asking us how many carbons are arranged in that planar geometry, and because the other 2 here are not, and this one here in the left hand side is, it means that the answer to this question is just the number 1, which is not too bad, nice and handy question, and it's something that comes up quite a bit in this type of organic question on the chemistry paper. So nice place to pick up marks. So for this question, there's a total of 4 marks going, and those 4 marks were associated with getting the number correct. And in this instance, the number was 1. And for me, in order to figure this out, I almost always would draw out this little diagram, the structural kind of shape, so I can actually visualize what's going on. So 1 was the answer to get full marks here. So moving on to part 4 here, we're asked to classify this esterification reaction as one of the following, and we're given 3 here to kind of choose from. 1 is a redox reaction, 1 is an acid-base reaction, and 1 is a substitution reaction. So all we have to do is write down one of these 3 reactions, which kind of classify the esterification reaction we looked at previously. Now, in the case of the previous esterification process, the correct answer here is going to be substitution. And that substitution can be seen when we are actually substituting out the water inside of when we're mixing the methanoic acid and the ethanol, we're seeing that the water is being substituted out. So that's why we're calling it a substitution reaction in this case. Thankfully, that was a nice and short question. So there was, kind of one of three options to pick from. And, I guess you have a 33% chance of getting it right. In this case, there was a total of 4 marks going. And those 4 marks, should I say, were just going for getting the right answer. In this case was substitution. So yeah, not too bad. Having a look now at part 5 here, we are asked another ester F, so this is another ester different to the one we found previously, has a glue-like smell and a structural isomer of E. We're then asked to identify F. Well, the first thing we have to note here is, what does a structural isomer mean? What is this structural isomer? A structural isomer is something that has the same general formula in this case, but it's going to be in a different shape, if that makes sense. So it's going to have the same number of carbons, hydrogens, and oxygens to the ester we found previously, but it's actually just going to be in a slightly different shape. So I've now just taken down the previous ester E that we were looking at. So just to label out, this here is ester E, and this is kind of the shape that we had determined it looks like. And in this case, what we know is this is what was it called, ethyl methanoate, and we're asked to give a structural isomer of this this ester here. Now there's a quick way, kind of like almost like a trick that you can do here, and it involves changing around our two groups. So remember we were saying earlier, this group up the top left is going to be where we get the methanoate part of our answer, and this group down the bottom right is going to be where we get our ethyl part. What we can actually do is, if we want to get a structural isomer, we can actually just swap the two of them and make a few little changes like that to get another completely valid ester, and then there's going to be, it's going to have the same number of carbons and hydrogens in it and oxygens, and that means that it will be a structural isomer. It'll be the same, but structurally different. So starting out here, we're going to be looking at this ester F, and the way that I'm going to do that is by swapping around the two parts of our previous our previous ester. So what we started out was we had this methanoate group up in the top left, and instead of having a methanoate group, we're now going to change that to an ethanoate group. So the ethanoate group is going to have 2 carbons, and it's going to be hydrogens dotted around them like this. So we're going to have a hydrogen there. We're also going to have a double bond going off to an oxygen, and another single bond going off to an oxygen as well. Coming off of this bottom oxygen here, we're going to have a carbon, and then off of this, we're going to have 3 hydrogens also. So here we have our newly drawn out structural isomer, and what we're going to do is kind of group the areas again like we did previously. So this is going to be our first one down here, and then our second one is going to be kind of this one over here. And similar to how we kind of looked at them previously, what we've done is, instead of having our methanoate group in the top left and our ethyl in the bottom right, what we've done is swap them. And what that means is now we're going to have a ethanoate group and then a methyl group. So we've just swapped them around, and that means that we're going to have to change the naming convention as well. So as I was saying before, kind of counterintuitively for a naming process, we need to start with this bottom right block here. So starting with the bottom right block here, we're going to have, this is going to have 1 carbon, which means it's going to have the methyl, it's going to have the methyl kind of a prefix, and then we're going to move on to our second block here, which is going to be the first one, and this is going to have 2 carbons in it, which means it's going to contain kind of the eth prefix as well. So this is going to be eth, and then following the naming convention of esters, it's going to be ethanoate, if I've spelled that correctly. So what we've done here is, we've taken our ethyl methanoate from, which was the ester E, and we've actually swapped around the two groups, and that has created methyl ethanoate, which is kind of just like the same thing with the name swapped around a wee bit. And after a while of doing a lot of these questions, you'll actually notice that all you have to do is swap them around in some instances. But personally, I like to draw them out because it's a little bit easier to visualize what's going on and actually understand how the naming works, because it's a pretty, sometimes I can get lost myself. So yeah. In this case, the required structural isomer is going to be methyl ethanoate. There was a total of 4 marks going for this question, and those 4 marks were for just getting the answer correct. So you don't need to draw out this thing like I have here, but personally, it just makes it a little bit handier for me to understand what's going on. But yeah, the answer that you needed to get there to get your full marks is methyl ethanoate. Now moving on to part 6, here we're asked to identify the products of the base hydrolysis reaction between the ester methyl methanoate and NaOH solution. So kind of a bit of a mouthful of a question and a lot of big words in there, to be honest. But in reality, what's happening is we're taking a ester here and we're putting it through the process of base hydrolysis. And what that means is we're mixing it with, in this instance, it's going to be NaOH. Now what's going to happen here is when we're mixing the methyl methanoate, which is this ester, with the NaOH, there's going to be kind of this reaction that takes place, and we're going to be left with some some products on the other side, and what we need to do is identify what they are and write them out. So not too bad. Now if you're able to do this, like just writing it down in terms of a chemical equation and then being able to identify it that way, that's perfectly fine. Personally, when it comes to organic, I prefer to take the visual route because it makes things just a little bit easier for me to understand what's actually going on. So in this case, I'm actually going to draw out the compounds that are reacting together and see kind of how stuff moves around. So drawing out what's actually happening here, what we're going to have on the left is our methyl methanoate, which is this kind of structural thing I've drawn out on the left-hand side here. It's going to be mixing with or reacting with our NaOH, and that's known as base hydrolysis in this case because we have the NaOH here. And what's going to happen is, and I personally like to draw it out because it makes it a little bit easier to visualize what's going on. But what we're going to be seeing here is the Na is going to actually be moving around a bit, and there's going to be stuff substituting in and out. And yeah, let's just kind of get straight into showing how those products are formed. So the first thing that's going to happen is going to be related to this methyl group here. So what's actually going to happen is this methyl group is going to be substituted out by our Na over here. They're going to be kind of related. They're going to be, one's going to be substituting in for the other one. So what that means is what we're going to be left with is the H is going to stay the same. It's going to be bonded to our carbon with a double bond up to our oxygen and a single down to our other oxygen. Now instead of having a methyl group attached to this to give us that methyl methanoate, what's actually going to happen is that Na is going to substitute in, giving us this kind of shape down here that I've drawn. What we're left with now, though, is going to be this OH over here on the right hand side, and we're also left with this methyl group now that is just kind of floating around. So these two things are going to naturally come together and form the other product that we need. So in this case, what we have is a methyl group mixing with OH. So what we're going to be left with is we're going to have our carbon here and our 3 hydrogens. So I'm just kind of drawing this. This is the methyl group. I've just kind of flipped it a little bit. And this is going to bond here with this oxygen and this hydrogen to give us OH. Now, this thing on the right-hand side is going to take a form of something that hopefully you're quite familiar with, and same for the left-hand side here. And we're going to use that and the naming conventions surrounding them to get the names that we need here. So what we have left here is the two products that we are required. Now we have them drawn out, which is not exactly what we're looking for. We're looking for the names, or you could even do the formula if you want, but we're not looking for the drawings. So what we need to do is condense them down into the names in this case. So let's have a look at this first one over here on the left-hand side. It does look quite a bit like a carboxylic, or not, sorry, not carboxylic acid. It looks like a lot like an ester, because what we just did is we actually just changed out the methyl group for that Na. And what that means is we can actually keep the same naming style for naming the compound. So instead of having methyl methanoate, we're going to be replacing that methyl group with this sodium here. So it means that we're going to be left with, it's going to be called sodium. And then the rest of what we have left here is going to be the same methanoate bit. So it's going to be sodium methanoate is what we have over here on the left-hand side. As well as that, we need to repeat the process for the right-hand side. So this product over here on the right. Now, this is hopefully something that's quite familiar to you. It's actually going to be an alcohol. And the reason that we know that is because of this OH group bonded onto it here. Now, by looking at the number of carbons, there's one carbon with 3 hydrogens bonded around it. That methyl group that we were talking about before, which means it's going to have the same prefix. It's going to have that meth prefix. Now, as following the same kind of naming style for all alcohols, what we do is we take that prefix and then we add on anol. So it's going to be methanol, and that's going to be our other in this case, our other product. So the required solution for both of for this question, should I say, is sodium methanoate and methanol. And you could also write down the formula. So you could say, for sodium methanoate, you could say HCOONA, and for the methanol, you could say CH3OH. They would be both completely acceptable, but in this case, I just like drawing them out because it's a little bit easier to visualize what's going on. So for this question, there was 4 marks going, and in order to get those 4 marks, you really did need to include both your methanol here and your sodium methanoate to get those 4 marks. And this is a little bit more of a tricky question, but I feel like it can be made a lot easier by drawing it out. Now, if you're able to write out the formula and the reaction and be able to balance it and be able to name them from that, that's perfectly fine as well. That's completely acceptable. But yeah, hopefully that was a little bit more kind of clear, the process that I was doing. So moving on now to part 7, in this case we're asked to explain why the boiling point of ethanoic acid, which in this case is 118 degrees Celsius, is significantly higher than that of methyl methanoate, which has a boiling point of 32 degrees Celsius, although the two compounds have the same molecular formula in this case. So what we need to do here is take a closer look at whenever you see boiling point or melting point, the first thing that should be going off in your head, alarm bells ringing, is how are the bonds? Are they strong? Are they weak? You need to look at them quite closely, because all of that is very, very closely related to temperature and the melting point and boiling point associated with stuff. So what we're going to do here is have a look at both ethanoic acid and methyl methanoate and see what differences there are there. So taking a look at kind of what I've drawn out here right now, the first thing that came to mind is I'm going to look at ethanoic acid. So this here is going to be kind of it might be a little bit strange, but this is actually ethanoic acid here, represented in a little bit of a strange way. So ethanoic acid is going to be just a portion of this big and scary diagram that I've drawn here. It's actually just going to be this little bit here. And the important thing to know about ethanoic acid is that the way that it kind of works, the way that it operates, is it takes this shape. And what we can see from this shape is that there's going to be a hydrogen and there's going to be an oxygen. Now, if we look at this, and just to kind of, I'll get rid of this purple line here, just to kind of look at it here, what we're going to see is there's going to be this hydrogen over here. So the first thing I'm going to note here is that there's this hydrogen here. And the reason that I'm going to note this is, though, despite the fact that it has this stable relationship, it has all the bonds it needs to be completely happy with itself, everything in the ethanoic acid is a stable arrangement, and there's actually something a little bit more going on behind the scenes. And if you recall back to how bonds work and electronegativity, what we know is that hydrogen actually has it's going to have a partial positive charge in this case, and the important thing to take away from that is that partial positive charge sometimes gets attracted to partial negative charges. For example, if you think about water, parts of the water molecule, the oxygens in particular, are partially negatively charged, the hydrogens are partially positively charged, so to say, and they cause hydrogen bonding to exist and stuff like that, which results in a higher boiling point. So looking at this kind of molecule drawn out, we have this hydrogen with this partial positive charge, and just beside it over here we have this oxygen which does have that partial negative charge. And because they're going to be, they have those opposing partial charges, it means that there's going to be a hydrogen bond created, which I've drawn in here in that kind of plum color almost. And what we see here is actually two ethanoic acid molecules. We have one over here on the left and we have one over here on the right. They're actually going to join together, because what we have on the bottom side is going to be the exact same situation as the top. We have a hydrogen over here with a partial positive, and we have an oxygen over here with a partial negative, and these are going to form hydrogen bonds. Now the process that this is, the process is also, it has a name. In this case it's going to be called dimerization, I believe, dimerization. And dimerization in this case results in the increased boiling point of ethanoic acid, which is one of the reasons why ethanoic acid itself has that higher boiling point. The reasoning behind it is that it does have hydrogen bonds. So just writing that down here, I can just say it down here as well. There's going to be hydrogen bonds present. Hydrogen bonds. So that's kind of all you really need to kind of talk about in relation to this question. I'm outlining, ethanoic acid. I'm showing that it has this undergoes dimerization. It's going to have those partial positives, partial negatives, and these hydrogen bonds, which will result in having an overall higher boiling point. Now, there was a total of 2 marks going for this question, and the reason there's actually so few going for it is because it's actually quite a tricky question. So there's really no stress if you couldn't remember dimerization off the top of your head. But you got those 2 marks for including even just this diagram, or a big thing would be the buzz terms dimerization, or even hydrogen bonds, which I have down here. But either way, it's actually not too bad of a question if you can recall the little diagram.